You are most welcome to this session of vector calculus. And this session, we are going to treat potential functions f. In the earlier video, we looked at conservative vector fields. We learned that conservative vector fields f are generated from potential functions through del or nabla f. That is how we define conservative vector fields. So there's a linkage between conservative vector field f and the potential function f. Del is defined as partial x, partial y, partial z when we are talking of 3 dimensions. And so today we'll be given a conservative vector field f, and we are supposed to generate the potential function. So we'll take an example. Quickly, this one can go off and take an example. So an example can be given f, that is the conservative vector field, to be xi plus yj. This is in 2 dimensions. Find f, the potential function that generated the conservative vector function. And so to do that, we know that f, conservative vector field or function, is the same as del f. But we realize that in this example, this is a 2 by 2 field f. And so in this case, we put in the value. It's defined as xi, vector xi plus yj. And then since this is a 2 by 2 vector, 2 by 2, partial x, partial y, then f. And so when you expand the right side, we're going to have partial f, partial x, I in the I direction, plus partial in the j direction. This is equal to x in the I direction plus y in the j direction. And so in this case, with this equation, we need to equate like terms. We're going to equate x, the I terms together. So the first term will be partial f, partial x equal to x. Let's say equation 1. The second one is partial f, partial y. Here gives us y. And so we can use to find f. Our aim is to find the function, potential function f. And so we can use any of them. We can use any of them. That is the 1 or 2. So for our purpose, let's say we choose the first one. From the first one, we realize that partial f, partial x equal to x. So if you cross multiply, what do we get? We get partial f is equal to x partial x. And so to get f, we need to integrate. When we integrate the left side, we integrate the right side. And so when we integrate the left side, integral differentiation will vanish. And so we have f, which is equal to, if you integrate x dx, we're going to have x squared over 2. And then after integration, we need to put in the constant of integration. But in this case, since it is partial integration, which we learned in our earlier video, it means that this function with respect to x. So all functions in y are constant. Therefore, our constant of integration will be a certain function in y. So we're going to get equation 3. Now, we have used only the first one. We have not used the second one. And so this is defined as s squared over 2. We need to find this function of y before we actually solve the problem. Then how do we get the function in y? We differentiate equation 3. If we differentiate equation 3 with respect to y, we're going to have partial f partial y equal to whatever you do to the left, you do the same thing to the right. So partial y of x plus h of y. This is what we are going to do. And so if you integrate, if you differentiate them term by term, if you differentiate x squared over 2 respect to y, you see that you're going to get 0 because there are no in x squared over 2. So just like if you differentiate the constant, you get 0. Now here, if you differentiate this term, I'm going to have differential of h of y respect to y, and that is partial f partial y. We can label these ones as equation 4. And so you see that, look at equation 2. Partial f partial y give us y, and the same partial f partial y partial h of y. So you can equate. So putting 4 equal to 2, what we have is that partial h of y partial y is equal to y. And so if we cross multiply, what happens? So we're going to cross multiply, then we'll have, you can put it up there, we're going to have partial h of y equal to y partial y. And so if you integrate the left side, you should also integrate the right side. So if you integrate here, we're going to have integral differentiation will cancel. You have h of y is equal to, if you integrate y dy, we know we're going to get y squared over 2. This time, this is a single function, single variable function. And so we are only integrating with respect to y. So therefore, integration, since a single variable function, our constant of integration becomes c. And so to put everything together, our f, which you got equal to x squared over 2 plus a function in y. Now we've been able to find the function in y to be equal to y squared over 2 plus. So when we put them together, then f, the potential function f that we are looking for, now becomes x squared over 2 plus h of y. H of y gave us what? Y squared over 2 plus our constant of integration. So when we have conservative function in 2 dimensions, this is how we find the potential function which goes with the conservative beta function. We'll look at example 2. In this example, we are going to look at 3 dimensions. And so, for example, given the conservative vector field as 2x plus yz in the I direction plus xz in the j direction plus sy in the k direction. Find f, the potential function. Good. And so, like we did for the 2 dimensions, the 3 dimensions will also be like this. So the solution is going to have f, which is a conservative vector field, is always defined as the del f. And so our del this time is 3 dimensions. So putting the values there, we're going to have 2x plus yzi plus xzj plus xyk is equal to the del. The del is partial x, partial y, partial z, all times f. And so if you open the bracket, you're going to have 2x plus yzi plus xzj plus xyk is equal to partial f partial x I plus partial f partial y j plus partial f partial z k in the k direction. And so, since the left side is equal to the right side, we equate them term by term. So if you take the first one, the I direction, we get partial f partial x give us 2x plus yz. You can label it as equation 1, and then we take the j direction. So partial f partial y will give us x and z in the j direction. We can also label it as 2. Then we'll take the last one, partial f partial z is equal to xy, which is in the k direction, and then we can label it as 3. And so out of these 3 equations, we are going to find f. So we're eventually going to use all the 3 equations. And so we can choose any one we want. Let's choose number 2. Let's choose number 2. So from 2, say using 2, what happens is that we can cross multiply. If we cross multiply, the left side we have partial f equal to xz partial y. And so if you want to find f, it means you have to integrate. So if you integrate the left side, you must also integrate the right side. And so if you integrate the left side, partial differentiation will cancel. We'll have f. And it's equal to, it means that we are integrating this term xz with respect to y. Xz is a constant. So the answer will be xz times the variable y. After integration, we need to have the constant of integration. In this case, since we are integrating in y, all functions in x and z are constant. So our constant of integration will be a certain function in x and z. We can label it as 4. And so we can differentiate with respect to, let's say, x. So if you differentiate that, we're going to have partial f partial x. It means that we're going to differentiate this whole term x, z, y plus a function in x and z, all respect to x. And so it means that if you differentiate it, what do you get? You are going to differentiate it term by term. So x and y are the constant. So we get z and y are the constant. So z and y can come out. Differentiate x with respect to x, you get 1. Plus, if you differentiate this term, you get partial hx and z with respect to x. Let's say equation 5. Let's say equation 5. So that's partial f partial x. Now, if you look at our earlier expression, we realize that partial f is, we have partial f partial x, which is 1, partial x, which is 5. They are the same. So we can equate them. So put equation 5 equal to equation 1. So we have zy plus partial h of x and z partial x, which is from 5. The same as 1, which is what? 2x plus yz. And so if you bring like terms to one side, we have partial h x xz partial x. We're going to have 2x is here, but we have yz. When zy and yz are the same because multiplication is commutative. And so when this one crosses the sign, we're going to have yz minus yz, which is 0. So eventually we're left with 2x. And so if you cross multiply, we'll have partial h of x and z S and Z equal to 2x partial x. Now we are looking for h of x and z. So what do? We integrate the left side and integrate the right side. If you integrate partial differentiation, it will go up. So we will be left with h of x and z will be equal to, if you integrate 2x dx, you're going to have 2x squared over 2, which is x squared over x squared. 2x squared over 2, 2 and 2 will cancel. We have x squared plus a constant of integration. So in this case, a constant of integration, which is g, will be a function in what y and z. And so we found h of x and z. So we plot it into this function number 4. So now number 4 will give us, let's quickly take off this one. So number 4 will give us f, the function f will be equal to x zy plus a function in h and x. Function in h and x will give us this, plus x squared plus g of y and z. So we can label this one as equation 6. And so we can also differentiate. We still have not gotten the function g of y and z. So we still need to differentiate this one with respect to z. So we will do differentiate to z, this function. It means that we are going to differentiate the whole term with respect to z, and that will give us x zy plus x squared plus g of y and z, right? This is what we are going to do. We are going to differentiate the whole term, right? And so when we differentiate this one, we have partial f, partial z, and that one will be, if you differentiate this one with respect to z, it means that x and y is a constant. And so we're going to have x, y, and partial z will give us 1. Now, if you differentiate x squared with respect to z, because there's no z term, x squared is a constant. And so if you differentiate a constant, you get 0. Plus this one, we get differentiate g of y and z with respect to z. So if we equate 7 and 3, 7 gives us x, y partial plus xy, let me quickly write it nicely. So xy plus partial g of y, z, partial z should be equal to 3. And 3 gave us what? Y, x and y. So we can quickly take it off. And so we can quickly take 3 off. And so what happens is that this one crosses the sign. So we're going to have partial g, y, z equal to, this one will give us 0. X, y minus xy is 0. So 0, if you cross multiply, 0 partial z. Now we are going to look for g of x, y, and z. And so if you integrate this side, go integrate this one, you're going to have g of y and z to be equal to, if you integrate 0 with respect to z, we'll get a constant c. You got a constant c. Go to get a constant c. And so we put g of y and z into this. So it means that our f will give us x, y, z, if you put it that way, plus x squared plus g of y and z. That gives us a constant integration. And so this gives us the potential function of the given conservative beta function. And so to wrap up, we have the potential function x, while x, y, z is giving us x, y, z plus x squared plus c. And so that gives us the potential function of a given conservative function in 3 dimensions. I hope you followed the example, and then with more examples, we work more examples, particularly in space 3 dimension, you'll be able to understand it better. Thank you very much for this presentation. Hope to see you in the next video. Have a nice day.